Good morning, AP Chemistry students. Today we're going to be taking a look at AP Chemistry questions number 4 and 5 from the 2019 exam. The reason we're doing two problems today as opposed to the one we've been doing previously is because in this particular case, these are short questions. These are the 15-minute questions that you will see on the exam, starting, or the style of 15-minute questions you'll see on the exam. And notice how there are only 4 parts to this one as opposed to the 8 you had on the previous question. It's a shorter question, so we should be able to do 2. That said, number 4, a student is doing experiments with CO2 gas. Originally a sample of the gas in a rigid, tells me that the volume is not changing, container at 299 K and 0.7 atmospheres. The student increases the temperature of the CO2 in the container to 425 K. First things first, A, describe how the effect of raising the temperature on the motion of the CO2 molecules. Well, we had an equation for this that we weren't supposed to memorize but was useful to talk about. And that equation is V RMS equals the square root of 3 RT M. This equation tells you the average velocity, or the root mean square velocity of a gas molecule, is based on the heat. As the temperature goes up, so does the RMS. And this is strictly speaking over the molar mass. There it is. Couldn't remember the exact phrasing of the question. But the important thing to note here is that as the temperature goes up, the velocity goes up. So as you increase the temperature, the velocity of the gas particles would also increase. The other way you can think about it is we talked about these graphs. You'd have different number of molecules at different temperatures. So this would be your speed, and this would be your number of molecules, and you'd have a curve here that would be like 200K, and then you'd have another curve here that would be like 300K, and then you'd have one more curve like so at 400K. Let's go ahead and label these. And notice how as you increase the temperature, the amount of particles spreads out, but the average temperature, this peak here, moves farther to the right. It moves lower, but to the right. This is representing the average. This RMS is this central peak for each of them. So for instance, on the red graph, it would be like so. Regardless, short answer, as the temperature increases, the velocity increases. Longer answer is the explanation why. Calculate the pressure, B. Calculate the pressure of CO2 in the container at 425 K. All right. This is a gas. We're talking about pressure. So the first thing we look at is the ideal gas law. And then we go, crud. We don't have the number of moles for our ideal gas law. We don't have the volume. We don't have the volume. We don't have the number of moles. We just have pressure and temperature. But we're talking about a change in temperature, and we're looking at the change in pressure. So what we're looking at is one of the other laws, Troyle's, Boyle's, Gay-Lussac. Take your pick. And if you remember, I told you you don't have to memorize those. They all come from the ideal gas law. So if I rearrange my ideal gas law really quick, I get PV equals R over NT. I just divided the N and the T to the other side. This always equals R. So if I put a little 1, 1, 1, 1 here, as this is always going to equal R. So on the other side, what I could do is do the same thing, P2, V2, N2, T2. And this combined equation here allows me to solve for any changing variables. So P1, V1, N1, T1 equals P2, V2, N2, T2. And this is the combined gas law that allows you to change for any number of changes. With this, we can also talk about how the pressure changes. How does this work? Well, let's go through this. Students did experiments with CO2 gas. Originally, a sample of the gas is in a rigid. Rigid tells me that the volume isn't changing. So in this case, the volume is the same, so it cancels out. If you'd prefer, you could also just erase it. But we're going to leave it on there for now. The student increases the temperature, so we know temperature is going to change of the gas. And we're talking about pressure, so that's probably also going to change. The number of moles isn't listed as changing. So since that isn't listed as changing, we then assume that it is held constant. So now I have P1 over T1 equals P2 over T2. And I can just plug in and solve. In this particular case, it started at 0.70 ATMs, which corresponded to 299 K. I don't know what P2 is, but I'm going to be looking at 425. I go solve for P2. Algebra, cross multiply, simplify if you prefer. And we get a number. Let me get my handy dandy calculator out. P2 equals 0.99 ATM. Once again, we're multiplying and dividing, so the two sig figs of the 0.7 are what we're looking for. And there we go. A and B. Okay, C and D. In terms of the KMT of the kinetic molecular theory, briefly explain why the pressure of CO2 in the container changes as it's heated to 425. So here I've drawn a rough representation of the CO2 molecules, the little dots here, and the directions they're heading with these arrows at the original 299 K. As that temperature increases, we've already said in A that they're going to start moving faster. So let's change these arrows to represent how they get faster. Okay? They start moving faster. Now, two things happen because of this. First, when you start moving faster, you're going to hit the walls more often. This is the time between hitting this wall and then it bouncing and hitting this wall is much smaller. And because pressure is a measure of how frequently and hard molecules hit the wall in a small container, as the frequency goes up, so does the pressure. Alternatively, because they're going faster, they're hitting the walls harder. Okay? Think back. Running into a wall or into a person going like walking down the hall pace doesn't hurt. Running into them full speed, well, that's football, and you need pads for that. So not only are they hitting it more frequently, they're hitting the walls harder. Both of these are valid responses. You can pick one or both. Okay? So, for instance, as the temperature increases, so does the velocity of the molecules, which results in them hitting the walls of the container not only harder, but more frequently, which then increases the pressure. D is asking about the KMT. It doesn't look like it is, but it is. KMT is broken down to three basic principles. The first is that gases in motion, or constantly in motion in random directions, the amount of volume the gas takes up relative to the space it is in is relatively small, and the molecules don't interact with each other. Those are the three assumptions that make the ideal gas law work, and they come from the KMT. Now, these are assumptions that don't match up with reality. If I have a CO2 molecule, it is very nonpolar. These are perfectly balanced here. But there is still an electron cloud. There is still this polarizable field around it. And there's still going to be, because of dispersion or London forces or London dispersion forces, take your pick, there's still going to be an attraction here. So instead of moving in perfectly straight lines like we saw here, there's going to be slight bends as they want to be closer to it. Okay? So there's going to be an attraction, a dispersion-based attraction. That will disrupt the ability for them to work perfectly as this. They're going to clump a little. Okay. And there we go. So let's put that in a full sentence, and then we'll be good to go. So the attractive forces between the CO2 molecules reduces the pressure or makes them behave like a non-ideal gas. The official scoring guidelines is the attractive forces between the CO2 molecules result in a pressure that is lower than predicted by the ideal gas law. There you go. C and D relatively quick. If you're doing this properly, you should be timing yourself. This should take 15 minutes. Check, see if you did this in under 15 minutes. If you didn't, try the next problem. See if you can do that one in under 15.